There's this skateboarding trick that only about 15 people have ever successfully pulled off. It's insane. It's a drop from a ramp into a full 360 loop, and it's so hard because you have to get enough speed to go all the way around, but not too much speed that you get slammed against the wall. 2 years ago, I was watching a couple more skaters attempt this at a live event with Tony Hawk, and Lizzie Armanto, who's a young and up-and-coming amazing skater, gave it a go over and over until the event ended. Then finally, at the end of the day, after everyone had left, she became the first female skater to ever successfully do the loop of death. So cool. What was working in her favor was physics. So today's lesson is going to be looking at situations like that, at the speeds and accelerations and forces for going into circles, like the perfect speed for going around a ramp in a car. And we're going to calculate that perfect speed. And we're going to calculate how you would make a spinning ring world in space that makes you feel like you're experiencing Earth's gravity. Today we're going to do that with math. Hello and welcome to Lesson 7 of Dianna's Intro Physics class, also known as AP Physics 1 Review, also known as Physics by Dianna. We're going to talk today about circular motion, which is a very special type of motion found everywhere, from toys to children to motion in the cosmos. We're talking a spinning coin or a record, all the way up to planets orbiting stars, stars orbiting the centers of galaxies, and galaxies orbiting each other. In this lesson, we're going to get to understand the forces that cause that circular motion. So put on your seatbelts because we're going to get dizzy. Today's theme, you spin me right round, baby. Right round. Okay, circular motion. Our first key idea is that for an object to go in a circle, there has to be a force. Think about it. Newton's first law says that in the absence of forces, you just keep going in a straight line because of inertia. Imagine you're driving down the street and you're going straight and then you turn left. What happens? You feel like you get pushed to the right side of the car, but did you really get thrown to the right? If you zoom out and you see what's actually going on, you're moving in a straight line and you would keep doing that, except that the car pushes you from the right. Maybe it's the friction of the seat, your seatbelt, or the door, but you get pushed or pulled to the left. This is just like the skater in the back of the truck that we saw in lesson 4, where the truck accelerates out from underneath him. If your door was open in your car and there were no friction, then when the car turns left, you would just keep on going right out the door. You turn with a force pushing you to the left in a circle. What direction does that force push? This is fun. The force is always in the same direction. Sort of. And a lot of people get this wrong. So listen up. Let's consider something a little simpler. Let's consider an egg on a harness attached to a string. Because my string has some fixed length, r, it has to go in a circle with radius r. But the egg has inertia and wants to keep going straight. We can prove that if we just let go of the string. Check it out. Straight line. Well, pretty straight. There just also happens to be gravity pulling on the egg. But before we let it go, the string exerts a force, a tension, on the egg, preventing it from going straight. And if you were on a string and someone swung you around, you would feel that tension as an outward force. But the free body diagram of the egg would show you a force directed straight towards the middle of the circle. That's the only way it can pull along the string. So that's the second key idea. When an object is going in circular motion, the force is directed inwards toward the center of the circle, always. Okay, now what about the magnitude or the size of the force? Let's figure that out by considering what you could change. You could make the egg bigger, then the force would have to increase to keep it going in a circle. What about if you spun it faster? Try it. I've got a cow on a string. I spin it slow, and then spin it faster, and I definitely feel the force increasing. What about if you change the length of the string? So this is going in the circle, and then I'm gonna have it going in this circle, and it doesn't feel like it's pulling as strong. What I was trying to do was get the cow to the same speed, and by speed I mean the linear speed of the cow, so the speed the cow is going around the line and not the angular speed that it's rotating. So yeah, we're spinning slower, but we're keeping the cow the same speed. All right. So now we have some clues about mass and speed and length of the string, and we can put that all together to figure out the force. So we know now that the force is somehow proportional to the mass and the velocity and inversely proportional to the radius. But that's not quite it. I'm about to do something really horrible where I flat out give you the equation without deriving it. Oh, let's get this stuff off of here. Whew. So, okay, force to keep you going in a circle is F equals mv squared over r. I'm just telling you and not deriving it because the cleanest derivation involves calculus, but if you're super curious, I'll do the derivation at the end of this video. So this concept of the magnitude of the force needed to keep something going in a circle was used to solve a bit of a mystery, or depending on who you ask, actually created one of the biggest mysteries of the last century. In the 1930s, this researcher, Fritz Zwicky, saw something weird about the rotation of galaxies. And in the 1970s, astronomer Vera Rubin saw it too. They saw that galaxies were rotating in circles way too fast for gravity to be able to hold the galaxies together. So they concluded that there must be extra mass that they couldn't see, and they called it dark matter. And we now believe that dark matter makes up 85% of all of the universe's matter, but we still don't know what it is. Crazy. But the point is, they found it using this concept of circular motion. So we have a new tool, F equals mv squared over r. Let's get to know it. Let's check the units. On the right side, I have m, which is in kilograms, and then v squared, so that I've got a meters squared per second squared. And then I've got my radius, which is meters. So one of my m's is gonna cancel, and I'm left with kilogram meters per second squared, which is a Newton. Excellent. That's the SI unit of force, so my units match. Amazing. I wanna take a second to point out, though, that just because my units match doesn't mean that an equation is right. You could still be missing a coefficient or some multiplication factor, but if the units didn't match, that means without a doubt the equation is wrong. So this force inward, which keeps an object going in a circle, has a name. It's called the centripetal force. So I'm gonna write a little C. This is the tool of the day. For any circular motion problem, I want you to remember one simple idea. For an object moving in a circle, the centripetal force F equals mv squared over r. If you see circular motion in a problem, think F equals mv squared over r. And if you need the acceleration, just write down from Newton, F equals ma, so our force equals ma, which equals mv squared over r. These masses on both sides cancel, and I get a equals v squared over r. That's worth pausing on, because the acceleration doesn't depend on the mass. If you're going around a circle with a set size, the r, and a set velocity, the v, then the acceleration for you is the same as it would be if you were the Rock, who is massive. We've named this force, but there's no like magical centripetal force out there. We haven't discovered a fifth force. In any given situation, there's gonna be a rope or gravity or maybe true love, some real force that's pulling inwards. And when this happens, we call it the centripetal force. And we should take a second to talk about another similar sounding term, the centrifugal force. This is a very controversial word. I just made some physics teachers shudder. Some people try to tell you that there's no such thing as a centrifugal force. It's a fictitious force, and that's not quite right. The centrifugal force definitely exists. If you've ever ridden the Gravitron, the best carnival ride of all time, where they're spinning you around and you stick to the wall and then the floor drops out from under your feet, yeah, you definitely feel a centrifugal force. And it's the push you feel if you're in a rotating reference frame. And if we're looking at the forces from that rotating frame. But a lot of people don't like that because it's not an inertial frame. But today, we're not describing the system from the spinning object's vantage point. We're describing it from the outside. So we won't be talking about centrifugal forces. It's all centripetal force from here on out. Okay, let's do a simple problem. Let's figure out how hard you would have to hold on if you were swinging something around. Think of like one of those fire dancers. Or when I was a kid, growing up in Hawaii, we used these things called poi balls. That was like a ball and a string that you swung around and tried not to hit yourself in the head. Or there's this sport that I just learned about called hammer throwing, which is crazy. So like that. Okay, let's say that we have a 1 kilogram ball on a 2 meter string, and we want to figure out the force. I'm gonna draw my ball right here. Here's my string, 1 kilogram, and this is 2 meters. So it goes in like a beep, 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 beep. It's not a terrible circle. And I swing it in a circle so that it goes around once every 2 seconds. So my time period is 2 seconds. What is the tension in the string? Well, first, what is the centripetal force? I say circular motion, you say F equals mv squared over r. I gave you the mass and the radius, but we don't know the velocity. But I can find it easily. The velocity is just going to be the distance the ball travels in one circle divided by the time it took to do that revolution. So velocity is distance over time. That's my linear velocity. And that's going to equal 4 pi meters. 2 meters times 2 pi, so 4 pi meters. And over time is 2 seconds. And so my velocity is 2 pi meters per second. I now have all the numbers that I need to calculate the force on the ball, forcing it to go in a circle. So my mass is 1 kilogram. And then I've got 2 pi meters per second, and then square that whole thing, and then that's over my radius, which is 2 meters. 2 pi is about 6, 6 squared is 36, divide that by 2, you get 18, and multiply by 1, and so my force is about 18 newtons. which feels a little bit like holding a 3-month-old kitten in your hand. Almost no effort. Okay. Sorry. Another great experiment for learning about centripetal motion is spinning a ball or a cow and a PVC pipe on a string with weights hanging off the other end of the string. Because when you spin the ball at just the right velocity, you can let go of the weights and all the forces balance out. Because the force of gravity on the weights provides the centripetal force keeping the ball going in a circle. This force is constant because the mass and gravity aren't changing. And if you pull the mass down to shorten the radius, then the equation says that my velocity has to decrease in order for the force to stay constant. Force is constant because the mass is constant. So what about the ball's speed as I shorten the radius? The equation says for a given force, as the radius goes down, the speed has to decrease, which we just talked about, but it looks like it's speeding up. It's a paradox! Or we just haven't yet distinguished between linear and angular velocity. This equation, v, refers to the linear velocity, or the distance per second going around the edge of that circle. Angular velocity is the number of rotations per second. So here we're making the radius shorter, so the circumference, or distance traveled, is a lot shorter. The angular velocity, or the rotations per second, may be increasing, which is why it looks so fast, but the linear velocity is decreasing. So we'll play around a little bit more with that relationship in lesson 13. Let's go back to our first example, a car driving down the freeway and then turning left. If you've ever driven on a curved freeway overpass, you sometimes notice that the road is steeply banked to the side. Engineers design the angle of that bank based on how fast they think the cars will be driving along the curve. So if you drive closer to the speed limit on those banks rather than racing through them, then your turn will be much better matched to the velocity they engineered it for, and it'll be so much easier. You'll also see these banks at circular racetracks and velodromes, and the purpose of that bank is to keep you from sliding off the road. How does this work? Well, let's start by thinking a little more carefully about turning on a flat road. You're on a road and you turn left. Here's my car, turning left. So what's pushing the car left? If you said friction between the tires and the road, you got it. If you live in a place where the roads ice up, then you've seen what happens when cars try to turn and there isn't any friction. They crash, fire, bad news bears. So what happens if we bank the road? Let's draw that. So here's our car, but on a bank at an angle. This looks a lot like a ramp problem. So we've got gravity pulling down, F sub g, and then the normal force, perpendicular, F sub n. Gravity and the normal force to the road each have components that need to balance out if the car isn't gonna slide off of the side of the road. So if you tilt too much or reduce the friction, then it is slidey time. And in case you had any doubt of whether I was cool, then I hope it's gone. Wait, the other way around. It's gone. Slidey time. But check it out. If the road is both banked and curved, then there's some component that's gonna push towards the center of the curve. So we've got a component in this direction. Beep, 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 beep. And we've got a component in this direction. And that is the force that's gonna help us turn. That's the centripetal force. We can even name it. But again, it's not its own force, it's part of the normal force. And that force is gonna have components normal to the road and parallel to the road, just like gravity. So here's a fun question. If a car is driving at some constant velocity around a perfectly circular track, is there some angle that we could bank the road at so that we could just get rid of friction and not have slidey time? So theoretically, we want to set it up so that we could just let go of the steering wheel. Our goal here with this problem is going to be to set up and solve an algebraic equation for the perfect angle theta, a bank angle theta, to match the car's velocity v. And we're in a circular motion situation, so we start by writing, if you get this wrong, I've failed. We start by writing down Fc equals mv squared over r. Our car has some mass, and r will be the radius of our turn in our circle, approximated as being the center of the circle to the center of mass of the car. And the force is directed inwards toward the center of that circle. Okay, next, free body diagram. What are the forces? Here is my car on a ramp. Gravity is acting on the car downwards, Fg equals mg. And so we have the usual components of gravity we're used to, a component normal to the ramp, that's this way, and a component down the ramp that would make us slide down if there weren't any forward motion of the car. And that component sliding down is mg sine theta. I know that it's sine theta because that component would be 0 if my theta were 0. Now here comes the fun part. It's a little tricky. That's an understatement. We're gonna look to set everything up to balance so that there's no sliding down the ramp, and we're moving forwards in a circle. So we'll have a centripetal force that points toward the middle of the circle. So I'm gonna draw that separately. Here's my centripetal force, and it's gonna be pointing toward the middle of the circle, so it's gonna be parallel to the ground this way, FC. And I can break that into two components, one down along the ramp and one normal to the ramp. And I can write that this component down the ramp is FC cos theta. And I know that it's cosine and not sine because if I take this to 0, then the whole centripetal force would be in that direction down the ramp. There wouldn't be a ramp anymore. Now we're done, because remember that the centripetal force is not the actual force. It's the name and model for the sum of all the forces that keep us going in a circle. And if I look at the component of it going down the ramp, it has to be the same as this component of gravity down the ramp, because there's no other forces. The only other force is Fn, my normal force in this direction, and there's no component of it in this slidey direction. And we said that we wanted no friction, remember? So this component of gravity must be equal to this component of the centripetal force. So that means mg sine theta equals Fc cos theta. What is Fc? It's mv squared over r. So I sub that in, so I get mg sine theta equals mv squared over r cos theta, and my masses on either side cancel, which implies that the angle of the bank does not depend on the mass. The angle should be the same for a giant SUV as it is for a scooter. So the fact that the mass doesn't matter makes it so much easier for engineers to make banked ramps. Thank you, physics. Now we can solve for the angle theta with respect to the velocity. So I get sine theta over cosine theta, which equals tan theta. And that equals my v squared over r, and I'll bring down my g. So tan theta equals v squared over gr. So the ramp angle would be different if you were on a different planet. Cool. So with no friction, if you're sitting still, you slide down the ramp. If you're going too fast, then you'll go shooting off the ramp. And if it's just right, then you'll go merrily along in a circle at this angle with this velocity. By the way, my head writer and I solved this in different ways, and he made me do it this way because he said that mine was the textbook way. But if you want to see the way that I did it, here it is. So now with his superior version, let's check the units. So we've got tan theta, which should be dimensionless because the tangent is a ratio of two lengths. V squared is m meters squared per second squared. And I've got g over r. We've got another m then on the bottom. G is meters per second squared. So we've got another meter, and then I'll bring my second squared up because it's meters per second squared on the bottom. So I get second squared up here. My second squared cancel, and my meter squared cancels with these 2 meters, and I get a dimensionless right side. Ta-da! It works. Great, done. What have we done? Well, we've shown that if you bank a curve just right, there's a velocity at which all the forces balance out, and you can drive with no hands. In effect, you feel like you're going in a straight line. And this is actually very analogous to an idea you may have heard in general relativity, where gravity curves space and time, but that's more confusing. You can just think about the space. And an object traveling in that curved space doesn't feel any forces. It just feels like it's moving in a straight line, but in curved space. And the effect is seeming like you're going in a circle. So when you get a cool result like this, it's always a good idea to test it out a bit. Play around to see if what you got makes sense. And a good way to do that is to test out the boundary conditions. I'll call this the extreme behavior method of sanity checks. Think about the extremes of your variables and how the model behaves. So let's play around with the angle and see what happens. Let's go to the maximum angle, a 90-degree bank. Something like this, where your car is at 90 degrees. This is the steepest that you could go. It's straight up and down. And as you approach the 90 degrees, tangent of theta goes to infinity. That makes sense because the steeper the angle, the faster you have to go to counter gravity wanting to make you slide down that steep ramp. That's kind of crazy. You have to go infinitely fast to keep going on a ramp at 90 degrees with no friction. So yeah, you can't do a 90-degree angle without friction, but you can totally do it with friction. So we can even play with g. So let's do the extreme behavior method on g and ask, what if g were 0? If the car were on a track with 0 gravity, well, anything over 0 corresponds to a tangent of 90. So without gravity, in order to turn, you would need a bank that is straight up and down. So if you're in space and in 0 gravity, then you could build a banked road like a giant cylinder. And if you flip that idea around, then a giant spinning cylinder can be used to simulate gravity. In fact, if you watch movies that try to pay attention to physics, like 2001: A Space Odyssey or like The Martian, then you'd see humans walking around in big spinning cylinders. In that rotating reference frame, the humans feel this centrifugal force, centrifugal, I said it again, but that's what they feel, pushing on them, and it mimics 1G. So you could take this idea even further. What if you built a thin spinning cylinder with a radius the size of Earth's orbit around the sun? If you set it spinning at just the right speed, you could have any equivalent gravity you wanted. So this artificial gravity makes it possible for these strips to have an atmosphere, which could form clouds and rain and make oceans and have enough space for an awful lot of people. So there's this classic sci-fi book from 1970 by Larry Niven called Ring World, where aliens build a world like this. And yes, we know, the ring world is unstable. So that's lesson 7, circular motion. When they ask what you learned on YouTube today, here are your 2 important takeaways. The force required to move in a circle points toward the center of the circle and is called the centripetal force. And when you see a circular motion problem, write down the magnitude of the centripetal force. Fc equals mv squared over r. But as an epilogue, as I promised, I'm going to derive the centripetal force equation, which involves a little bit of calculus. And this derivation will be actually quite similar to the one for springs and swings and things that are oscillating, which shows up a lot in physics. R vector equals r times cosine omega t x hat plus sine omega t y hat. And then I take the derivative of that, and that gives me my velocity vector, which is r times negative omega sine omega t x hat plus omega cosine omega t y hat. And then the acceleration is the derivative of that, so my acceleration vector equals r times negative omega squared cosine omega t x hat minus omega squared sine omega t y hat. And if you just pull out the negative omega squared, then I get acceleration equals negative omega squared. But then I have a cosine, and then I have a sine, and I'm back to the r vector. And the negative tells me the direction of my acceleration. It's inward. Here's my motion in a circle, here's my radius vector, and that's outward. So my acceleration vector is gonna be inward. Cool. And then because F equals ma, another fact of life is that omega is your linear velocity over your radius. So we've got all of this together. I can sub this in here, and so I get the magnitude of my acceleration equals this squared times r, so that's v squared over r squared times r equals v squared over r, and then I sub that in over here, and I get F equals mv squared over r. Ta-da! And that's it. We're done. Very cool. And because you can only really learn physics by doing the problems, here again are all the problems we did in the lesson, and you should definitely go work them again at home. And now I get to share some crazy physics. I'd say that the most amazing place where circular motion shows up is around a black hole. Back in 2019, that's like a year ago, but maybe when you're watching this, it's many years ago. In 2019, the scientists of the Event Horizon Telescope collaboration published the first ever image of a black hole. I made a video a couple years ago where I was like, we've never made an image of a black hole, and then boom, we did! You've probably seen it at this point. It looks like an orange donut. That orange frosting is what astrophysicists call the photon orbit. The black hole's enormous gravity bends light. Yes, it bends light in approximate circular motion around the event horizon. So think you can calculate the force bending the photon? I mean, we have been saying all this time that F equals mv squared over r, but photons have no mass. What? If you keep on with physics and decide to take a course on general relativity or something, you'll learn how to calculate the motion of light moving in circles and figure out why you don't need mass. I hope you do keep studying physics. And now a message from a very special guest.
Hey, it's me, Derek from Veritasium, and you are embarking on a physics journey. You know, when I was a kid, my mom told me that physics was all about finding the right equation and putting numbers in. And yes, that's definitely part of physics, but it's so much more than that. It's about finding a consistent, coherent way and process of understanding everything in our universe, including the stuff that like we kind of know is there, but we can't even see. And you are embarking on this journey. You are incredibly lucky to be getting into it with Dianna Cowern, the physics girl. She is awesome. So really, I think you are going to have the greatest time in this course, and I just wish you all the best in your physics journey, because for me, it was life-changing, and I hope it is for you as well.